Good morning, IBC. I'm Dickon Ross, Editor-in-Chief of Engineering and Technology magazine. And welcome to our first session of today, which is entitled, Hey Radio, Tell the DJ I'm Stuck in Traffic. And we'll hear today about the evolution of radio with voice-controlled digital assistants, which seems ideal for the car listening of the future. And we'll hear about a new system to deal with the myriad different ways in which you can now interact with the studio. But first, we have Jorma Kivelä, who is CTO and co-founder of Jutel Oy in Finland, and his talk's entitled Flexible Virtualization of Radio Production and Playout. And he's going to tell us about his project, whose ultimate aim is to run a local studio in a shopping center, sports center, school, or wherever, with just an internet connection and decent acoustics.
Thank you. So I'm Jorma Kivelä, CTO of Jutel in Finland. Jutel is 35 years old company, specialized in radio automation, especially for larger networks, larger national broadcasters. The business driver for this project has been to bring radio close to the people, and also to make deployments of temporary local installations, local studios, that kind of make it simple. And for that, the main goal has to build up a virtual browser-based radio production and playout in cloud environment without any dedicated hardware that is needed in studio or playout infrastructure. So as simple as it can be. And the idea is that we can build a local studio or a local temporary radio station or multiple spots in some sports happenings or wherever something is happen, just so that we take a laptop or a tablet, have a some decent acoustics and internet connections. For some cases, there can be local microphone management if there's multiple speakers or something like that. And the main goal here was to utilize as much as possible the existing building blocks, so that to use backend tools already in cloud for radio production, planning, that kind of stuff. Then what we had to do is we had to add mixing, audio processing functionality within the cloud, and also to have those controlled at the user premises. And in all, there's multiple sub-goals. For temporary studio installations, we wanted to have no extra hardware needed, except the microphone inputs, just a workstation with a browser. For regional studios, there needs to be a minimum or no extra audio hardware, just for instance a USB mixer, and naturally some acoustics. And for remote broadcasts, we needed to arrange so that the whole thing can be run with a tablet, so that from the tablet we take the audio via mobile interface, internet, or via mobile codec. And then the same approach, same user interfaces can also be used in larger studio environments with so that it is integrated with touchscreen virtual studio controls and IP audio AS67 routing. For reporter work, we needed to bring browser-based reporter tools so that no specific client software needs to be installed. And the on-air playout so that it's very flexible, so that the playout engine can be in a traditional studio, or it can be in the central computer center, or it can be in a cloud with streaming interfaces. And the audio management, audio routing needs to be flexible for different kinds of installations. For data model, we wanted the system to be backwards compatible with the existing quite large installations that exist. I think the largest is about 2,000 workstations. So the system architecture, what we built up. Firstly, we decided that USB audio is going to be used in the user end. We will be using cloud. For test purposes, we choose Amazon AWS. Naturally, it can be also other cloud vendors, and also it can be in-house infrastructure or in-house cloud. The backend is the existing web architecture-based backend we have, which is already running some national channels and is proven, and it's all based on modern web architectures. For the user interfaces, we wanted to have browser user interface for all the functionalities, to use HTML5 so that no add-ons need to be installed in browsers, and we can use several different browser vendors for the same thing. For the audio or interface between the user end and the server, there's REST APIs, REST for the screen control and that kind of. For audio transfer, we choose to have WebRTC with Obus audio. The reason for WebRTC is that it's today built in the browsers, so we need no add-ons installed in the workstations. And for fast messaging and fast control, there's active MQ message bus. And for Playout, there's the Playout engines, Playout servers that are in the cloud, and then there's the built-in live mixing facility, which is also placed within the cloud. And for this project, we used the output streams with tested WebRTC, IceCast, and RTP transfer. And if we go more technical, the system architecture shown here shows a typical web architecture with dual or redundant back-end load balancers. We can have actually multiple back-ends running. There is the databases, file storages, they can be run also from the cloud or from local services, and there is the active MQ message brokering for playout controls and that kind of stuff. And then there's separate processes as playout live servers, playout mixing services. And the whole thing here was built in Amazon cloud. The system was at the point of tests installed in AWS in Ireland. We had also an in-house system built in virtual environment in a major broadcaster in Finland, and then we had some other test installations. The system that was built up contains all the major functionality that is needed in a large broadcasting environment, so that there is also all the long-term planning, short-term planning functionalities, music searches, music interfaces, traffic. Also, it can be interconnected with MOS news programming. And later on, we added also browser-based multi-track audio editing. There are also script tools included. And we run these tests in both indoors, outdoors, in fixed facilities. And so some of the tests run as a local studio installations. Then we had, for instance, one test setup, which was so that there was one point was in a fixed studio, the other was a guy at his home, and then one guy was at the beach with a laptop, and it went all well. The functional results of those tests and of the system is that it can be used very well for live broadcast production purposes. Naturally, also pre-recorded or automatic playout can be utilized, but that's not the main goal here. The on-air playout control and audio monitoring delay was found to be small enough to be used for this kind of radio production, for semi-assisted with music, jingles, talk, and that kind of things. We also tested the system with separate contributors or systems, multiple systems addressing the same programming in different locations. With this setup, we had during the tests, it made so that all the audio was routed via the server environment. So what it means is that we actually get the delays from one user to the server, from server to the other user, and then speech back. That was slightly annoying. So what we are doing now is that we are putting the chatting audio directly between the users in chatting environments. The test results in technical sense was that what we used was Opus audio coding with various bit rates from 48 kilobits to 256 kilobits per second. It doesn't actually have a lot of change in the delays. The playout start delay, so that you have the playlist, on-air playlist, and you start the playout from a remote user interface. It's very small, so it's on the order of the network ping or half of that. So that's not so important in this case. The total delay from the server playout to the listener in network was found to be about 160 milliseconds. And if we think what's the total delay from a microphone of the presenter to first to the server and then from server to the end user, it was found to be average about 300 milliseconds and varying between 280 and 450 milliseconds, depending on the test times and so on. This is not optimized in parameters or in buffers or that kind of stuff in any way. So these were the first results of the system. But still, with these delays, we can live with the application and use case. And then if we go to the conclusions, this kind of cloud-based production audio mixing, it can be used for live radio. Some use cases here is simple studio installations for radio networks. What this means is that it's very easy to just build up a small studio facility so that you have some acoustics and some internet connection and microphones, and that's it. We can have multiple studios to the same programming, and we can also mix this with the main studios, for instance, at the broadcaster's headquarters. Then one use case for this is temporary studios and temporary radios, so that we have cloud or let's say radio systems already ready in the cloud, and if somebody needs a temporary studio or temporary radio, it takes about 15 minutes to build up the whole system from scratch. Then we can have this as a local studio for larger network. Also, there's been talks on, because there's in many cases a regional or local studio needs to be moved away for renovation purposes or something like that. We can replace that with a cloud solution for the duration of the renovation or perhaps permanently. And we can have a combination of large IP-based studios and small contribution units. Naturally, also sports events, if you have lots of places, you want to have local transmissions. And there's also possibility to because of the REST API interfaces, we can very freely make new kind of user interfaces so that, for instance, some user could have just a couple of buttons and a green light on on a phone screen, and that would be the whole thing for contributing. Or we can just send a URL for someone to interview by email, and from that URL the person can be interconnected to the broadcast. Further steps, what we have planned is to have lots of different use cases applied to integrate IP telephony into this cloud version. We already have this IP telephony integrated in IP-based studio environments with these browser-based tools to optimize delay topics, and then to introduce this also for mobile use in a better way, so that we can use bonding technologies for the mobile interface, and also to have better tools for distribution to transmitters, so that instead of a codec or RTP connections, we would use SRT or RIST protocols, and these are already supported in the software, but they have not yet been tested. So that's shortly the introduction for this. Thank you.